Hey everybody, welcome to another Welding Wednesday. This is Intro to GMAW, Part 1. So we're going to talk about this one, kind of the background GMAW, what is it, and then equipment. For Part 2, we're going to talk about transfer methods of GMAW and then also troubleshooting. So my kind of goal in this two-part series is to kind of go through some of the common things that I've seen when people have trouble with GMAW, and then how I go through the process of kind of like troubleshooting, what to look for, that sort of thing, just to help you all get a bit more knowledge base with this process. But right, there we go. So we're going to talk about background and equipment today. So starting off with background. Cool. There we go. All right, so what is GMAW? Stands for Gas Metal Arc Welding. It's a wire-fed arc welding process. So you have this gun, which we can see up here. You squeeze a trigger, out will come electricity, wire, and shielding gas. It's known as a semi-automatic process because you squeeze a trigger, machine provides all those things, and then you provide the travel. So if we compare it to like a manual process like SMAW, the machine will be providing your electricity, but you're providing the feeding of the wire and all of the travel in the joint. Some common names are MIG, so you'll hear that a lot. That stands for metal inert gas, and then MAG, metal active gas. So metal inert gas is not really correct anymore, because we do not use only inert gases, but still very common shorthand. You'll hear me use both interchangeably, but the correct name is GMAW. And then MAG is something that I've seen in like Canada, but also in Europe, a lot in Europe. It's very widely used. Man, I would say out of all of our customers, if I just think about GMAW, I don't know, maybe 70% or more do GMAW wire feed process. I mean, it's super, super popular because it can do a wide range of different thicknesses, positions, that sort of thing. Very popular in industrial environments, and the majority of all automated welding will be using a wire feed system. So development, 1948, started to get developed, first used for non-ferrous materials, so like aluminum, but the high cost of inert gases prevented the extensive adoption of the process. 53, they started using CO2 for the welding atmosphere, which made it much cheaper and opened it up to many more people. Then in 58, short arc was released, so also known as like short circuit. That increased the versatility of GMAW because now you could use it on very thin materials. And then 1960s to today, we started the spray transfer process. Again, we're going to talk about those next week or the next time on the next session. And then we had new gas mixes, stuff that we use today like 75-25, 90-10, 98-2, those sort of things. And then also pulse, which allowed for current manipulation and allows GMAW to be used in more places, positions, that sort of thing. All right. Keep rolling here. Okay, let's look at our equipment. So here we have kind of like a basic-ish GMAW setup, or at least one you'll see a lot. So we have our power source. On this other side, which you can't see, there's a door where you open it up, and that's where your spool of wire will be that you'll use as your filler in your electrode. Got to use shielding gas with this. So unlike stick welding, you need external shielding gas. There's nothing internal. There's no flux, anything like that. You have your work lead like normal, and then here you have your gun lead. And there's your gun, and there's your trigger to be able to squeeze, dispense that stuff. At the end of the gun, you'll have contact tube right here. That's where electricity gets added to the wire. You have your nozzle, which directs the shielding gas into the weld zone. Diffuser is what puts your shielding gas into the nozzle. So you squeeze a trigger, out will come electricity, out will come wire, out will come gas. And then you, again, just provide movement down the joint. All right, here's a more kind of exploded view of that equipment. So we have our power source like normal, work clamp, there it is. And now we start to get a little different. So we have that extra shielding gas, we have our filler material. You're going to need a filler or like a wire drive of some sort. So that's going to be extra equipment to actually push the wire through the system. And then we have our, again, gun at the end of our work cable, gun cable, which will, again, dispense that electricity, filler, and shielding gas. For your power sources and polarity, so it is a constant voltage source. If you remember from our last time when we talked about electricity, constant voltage means that when you're running it, your voltage does not change a lot. You can adjust your amperage by increasing or decreasing that arc length while you're welding. Usually has faster welding on the filler wire, and then increased penetration and welding speed. So some advantages of that DCEP, positive polarity, also known as reverse polarity. AC is rarely used in these units. We have our wire feed system. So oftentimes this is internal. The wire feed system works off of 3 different ways of dispensing the wire. You can have a push, you can have a pull, or you can have a push-pull. So what happens in these wire feed units is you have drive rolls like these, and the drive rolls will provide pressure to the filler, and then will either push or pull it through your system. Here you can see on these drive rolls, there's 2 little grooves. A lot of times, a set of drive rolls will have grooves for 2 different sizes of wires. So 035, 045 is a very common one. That's very common in industry. And when you're doing it, you'll see a stamp on the side that says 035. You have to make sure of how your rollers work. But for a lot of them, if that 035 is sticking out at you, or you can see the 035 in this case, that means that the wire will be in the 035 groove. So, in addition, on Lincoln machines, they have this guard right here, which helps to prevent bird nesting. So bird nesting is when there is there's an issue with steady feeding of your wire, which can happen 100 different ways. And so inside the machine, the spool will still be turning, but there won't be the wire being able to move out of the end of the gun. So it just collects inside the machine and does what's called a bird nest, because it looks just like a bird nest. So push is the most common feed system. It pushes the electrode through the liner to the contact tip. It works great for shorter cables and for stiffer wire like steel. Really struggles with softer wires like aluminum or those longer leads. A pull system pulls the wire through the liner, and the whole drive motor system is located in the gun. Great for soft wires. Limitations are usually heavier and bulkier in your hand. Push-pull is a mixture of both. That's ideal for long cables or with soft or small diameter wires. More expensive and complex setup, but if you're doing aluminum, especially a lot of wire feed aluminum, you're going to want a push-pull gun, because it's going to give you the very best consistency for your feeding. Just make your job way simpler. Here's a picture of an internal drive roll system. So that's number 1, and then one that's in the gun. So just to look at some of the parts here, we can go ahead. These are rollers. So there's 2 sets of rollers. Here is our tensioners. So 2 of those tensioners also. So the rollers and the tensioners, rollers are again going to push the material. The tensioner, you adjust according to the size of the filler. One of the most common mistakes I see that people make constantly is over-tensioning your filler. Over-tensioning your rollers. And so what will happen is you'll either crush your wire, especially if you're doing something like a flux core, or you will go ahead and actually, like in the previous slide, you might have seen the rollers on the upper right picture. They had there was like a U groove, a V groove, and then a V knurled groove. And that was for different types of wire. If you overtension, you can turn like a V into a U groove by putting too much pressure. Things like the knurled V groove are there for like flux core, because if you remember with flux core, you have a wire, so the outside is metal and then the inside is flux. If you overtension in this system, you'll actually squish your wire down, and that will cause fading issues for sure. Looking at this setup again, so this is where we're getting power that will be put into the wire, and then here is where our hookup for our gun lead is, and then this little twisty screw helps to lock the gun lead in place. If you do not know how to tension wires in your system, really make sure that you're either talking to somebody who does and having them help and show you, or just watch like another YouTube video or something on it, because again, I see it all the time, and it can be a real issue, and it's not too difficult to do right when you set up your machine. All right, this one, number 2, is an internal like gun system that's very much like the one that's in the machine, just a much smaller scale. So here's a roller you can see here. So instead of being like vertical, they're horizontal. But the same type of principle, you have your tensioner, you got wire inlet guides, outlet guides, that sort of thing. So same setup, just smaller scale, and your gun. With GMAW gun, what that does overall is that's what you hold in your hand. That's what you control during the welding operation. And again, delivers wire, shielding gas, and electricity. So there's going to be a bunch of different like styles. You can get a million different styles of necks and size and length and the size of nozzles and all that sort of stuff. The key components are going to be your trigger, which is right there. So that's going to control the arc initiation and the feeding of the wire and the shielding gas. You have your contact tip, that's at the very end here, also known as the contact tube. I use tip mostly, but tube is completely acceptable. And that's the part that transfers the electricity into the electrode. So the electricity is not added until the very end, which makes sense, because if you added it before in the system, you're going to lose some power due to resistance, and also, you'll have the possibility of like arcing in your system somewhere, which you don't want. The nozzle, so right here, that's what directs shielding gas into the weld area. And then finally you have your liner. Liner is the guide for the wire through the feeder and the gun cable. So when it comes to like operating a MIG system, I'll say, unless you're doing like extremely heavy work, guns last a really long time. You might not actually ever have to replace the gun. The things that need to be replaced are the liner and then these consumables usually, which is the contact tube and the nozzle. Gas diffusers also, they're like consumable, but they last a really long time. Here's a more exploded view showing these components again. So here we have the trigger. Here we have our like housing. So right down in there at issue. We have our necks right there. We have diffuser right there. So diffuser is where the gas gets put into the nozzle. Here we have a contact tube. There's different ways that you can set up your contact tube, your nozzles. Like, there are so many really variations of different types of setups for your lead, and you can get really, really specific based on what you're using it for. Then we go back a little bit through the system. Here's our cable going back into the machine. This is our liner right in there. So you can kind of see how everything fits together. But the main takeaway I want you to get from this is there's a lot of places where something can go wrong, which is important when we're troubleshooting. Shielding gas. So we've spoken about shielding gas before, but it's particularly for GMAW. It protects your molten weld pool from the atmosphere. The key things it does is it makes your arc more stable, helps penetration, helps with bead shape, helps with spatter, and then also determines which transfer method you're using. So really important stuff. This is one of the reasons why it's kind of difficult to do a GMAW like outside of a shop sometimes, because if you have a wind over about 3 miles an hour, you can blow away the shielding gas and then you're not going to get the right coverage. The other thing you have to be careful of is even if you're in the shop, if you have your welding too close to an exhaust system, depending on what type of exhaust system it is, it can actually pull off that shielding gas, so it's not able to do its job either. So just something to watch out for. Some common shielding gases. We can see here we have like 100% gases here, and then we have our blends or mixes, 2 gases, 3 gases, and then this chart's kind of nice because it shows you what it can be used for. So if we look at our like most commonly used gas, I would say, would be a 75-25. So 75% argon, 25% CO2. Now, I have an issue with this chart, so we're going to talk about it real shortly. So this chart says you can use it for stainless, you can use it for steel, you can use it for magnesium. Magnesium, I don't know. I do know you do not want to use it for stainless. You don't want to use anything with more than 5% CO2 for stainless, because what will happen is too much carbon dioxide will help with sensitization of your stainless. And basically what that means, and we'll learn more about this when we talk about materials later in the year, but with sensitization, you go ahead and when in between a certain temperature, so it's like 800 to 1500 degrees Fahrenheit-ish, basically your chromium can come out of your solution of your stainless steel, and it very readily combines with carbon. And when you combine those two, it creates chromium carbide. Once chromium carbide is created, that doesn't break apart again. So now that is a new compound. If you've done stainless steel welding, you probably have seen this before. They call it sugaring. It looks like crusty brown sugar kind of on your weld. And once you take the chromium out of the stainless, it's no longer stainless. So it's a big deal. So to be able to try to minimize that as much as possible, you want to use less carbon dioxide. So over here, we have blends of 3 gases. Very common one is known as trimix. So that's argon, CO2, and helium. That's really great for stainless, but helium is very, very expensive. So another thing that works well for stainless is a 98-2 mix. And 98-2 of either argon oxygen or 98-2 of argon and CO2. Let's see, do they have a 98-2 here on? No, but it would be argon and then less than 5% CO2. And either one of those seem to work pretty darn good for your stainless steel. You might need a trimix if you're doing some special application, or if you're doing thicker things, because helium really helps with getting more heat into your workpiece. But again, very expensive. So overall, if you're just doing kind of run-of-the-mill stainless steel welding, just nothing special, thinner material, 98-2 will work great for you, save some money. Down at the bottom here, you can see just an example of how much mixes can affect like bead shape. So, argon CO2, argon oxygen, you get this crown in the middle and then kind of dips on the sides. Argon CO2, same thing, but it's flatter. Carbon dioxide, very flat weld. When it comes to your electrodes, again, we talked about this with filler before, but a quick review. It's called an electrode because it's going to conduct electricity into the weld arc. It's also filler. So with GMAW, your filler and your electrode are the same thing. The filler provides strength for the final joint. Other types of welding processes, like GTAW, you can go ahead and do what's called autogenous welding. So that's when you're just adding energy and you're melting the base metal together and you have no filler. Can't do that with GMAW. You need filler. So it provides strength for the final joint, helps fill up gaps, make sure that weld is nice and smooth, no big interruptions, places where, stress could concentrate and break it. And then it makes up the majority of the final weld joint. Breaking down the classification system, so this is AWS classification. If we look at this, we have ER on the front, which means electrode and rod. So what's interesting about this filler is this filler also works for GTAW. So electrode means that it can conduct electricity through it. R means it can be cut to rod length. So E, electrode, spool, fed through the machine, filler, conduct electricity. We could take the stuff that's on the spool, cut it into lengths, like 36-inch lengths, and use it as GTAW rod. So if you know someone who's in a pinch, or you're ever in a pinch, and let's say you're doing some TIG welding and you run out of steel rod and you're like, oh man, I don't know, and your distributor's closed and you just can't get any. If you have GMAW rod, same exact thing. You can just cut off a piece, as long as it's the same classification, cut off a piece, use it, shouldn't have an issue at all. The next two here, where this is off just a little bit, but that's your tensile strength in 1,000 pounds per square inch. So that's minimum tensile strength in this case of 70,000 PSI, which means if you weld it correctly and you follow manufacturer's directions on how to weld it, it will take at least 70,000 PSI to pull it apart. Then we have S is solid. This is to distinguish from like a flex core. Anybody out there remember flex core? What letter is used for that? Give you a second. The letter T. So that stands for tubular. And for those of you who are old like me and watched Ninja Turtles, cowabunga. And then finally, the suffix here is going to be your chemical composition and shielding gas. So two very common suffixes that are used is a 70S-2 and 70S-6. So I don't have that on here as far as what they mean. This is memory, so try not to steer you wrong here. I believe the -2 has more deoxidizers than the -6. So -2 is good if you have like dirtier metal, that sort of thing. Or maybe dirtier is not the right word, just more chances of contamination. And then maybe it's, okay, I'm taking a step back. 2 and 6, the differences are one of them has more silicon, one of them has more deoxidizers. I think -2 might have more silicon. And so what that means is that it flows easier. So it's easier to control the filler and it flows better. And then the 6, I believe, has the more deoxidizers. But hey, here's a game. Go ahead, look it up, see which one's which. So yeah. Here's my resources I use for this, as always. If you have any questions, concerns, comments, let me know. Here's our locations. You can get a hold of me by calling our main location here at Minneapolis and asking for me. Or I don't put my email address out there usually, but I'm not hiding it. You can always email too. So it's rskattum@mplso2.com. Let me know what's up. Let me know if I got the -2 and -6 wrong. All right. Appreciate you folks paying attention here with me, and you will see part 2 next. All about technique and transfer method. All right. Thanks, everybody. Catch you later.